Okay, we consider area integrals and other integrals in polar coordinates. Now in polar coordinates, we have, of course, coordinates r and theta. So typically, we'll start by partitioning our theta interval. Now what I've got here, it appears to be a circle. It's a little irregular. It doesn't have to be a circle. We have points on and within this boundary for all values of theta from 0 to 2 pi. That's not always the case. We could just have the upper half of the circle or the shape, whatever it is, the shape, the portion going from theta equals 0 to theta equals pi. Or we could have a slice from here to here, maybe from theta equals pi over 2 to theta equals 2 pi over 3. And we don't necessarily have to have a constant boundary on our, a constant value of r on our radius. However, we'll worry about that when we get to integrals that involve that, okay? So, what I've done here is I've just divided things up into theta subintervals, okay? For this wedge here, as for any other, theta has specific boundaries, constant boundaries. Theta goes from one value here, here it is, okay, a little over pi, a little over 180 degrees, maybe 200 degrees, to some other value here. Now we're not going to even think in terms of degrees when we do integrals, because then we have all kinds of conversion factors. We think in terms of radians and we work in terms of radians, so we don't have a bunch of conversion factors. Okay, I guess that'd be a royal pain. Okay, well anyhow, so typical interval goes from some constant value of theta, a radial line, a line from the center, straight line from the center at some angle theta, to some other line at some other angle theta, and you have a delta theta within here. Now, I didn't label a delta theta, and I don't see a good piece of yellow chalk, but I got this big one. So, we could have we would have a delta theta if this is a partition from theta equals 0 to theta equals 2 pi, or any other partition. This would maybe be a delta theta sub I. And we'd have a theta sub j star, the angle of some angle between here and here, a line somewhere within this wedge. So we'd have a theta sub I star, and everything is going to proceed very much as it does with rectangular coordinates, but there is one little catch. Okay, well, so this would be the portion of whatever our region is corresponding to the ith slice, okay? So our theta, in this case, would be partitioned from 0 to 2 pi, and our partition would be, well, theta naught is going to be 0, theta sub n is going to be 2 pi, and we're going to go from theta naught to theta sub n. Some interval theta sub I, our sample interval in between. Or some ith interval with sample point theta sub I star, sorry. Okay? Now, that's the region we get with constant boundaries on theta, and that's the kind of region we get when we partition theta. Now, if we partition R, okay, so R is going to maybe, for this region, go from 0 up to something here. It doesn't have to start at 0. There could be a hole in the middle. And it doesn't have to go the same distance on every theta interval, okay? But for any r between 0 and wherever r ends on this particular slice, you're going to want to partition r. Okay, so we partition r on this slice. Now, I say we partition r within the slice, and I want to be consistent with what I did before, so I guess I want to put subscripts on these. We're going to partition r within the ith slice, so we're going to have an m sub I here. We're going to do m sub I r subintervals that extend from here out to wherever r ends for this value of theta, theta sub I star. So there's our partition. And between two values of r, well, we're going to be between two concentric circles. So it's as though, now I'm going to mess up this picture, so I hope you enjoyed it while it wasn't messed up, but here's a circle corresponding to one value of r, and here's a circle corresponding to another value of r close by. So we think of this as, I'm looking for the name of this thing, like a hoop, but it has two dimensions, an annulus. Okay, so anyhow, this thing has some radius that I'll call r sub ij, because remember, theta has already been partitioned on the index I. R is going to then, for that theta sub I, be partitioned on index j, so that r's go from, well, we talk about the jth r interval. So this would be the jth r interval. Has radius r, I sub j, sample point, r sub ij star, and width delta rij. So the width is this, the sample radius is r sub ij, that goes from the center here out to some point or some radius between these two, that's our r sub ij. And a width delta r sub ij. Okay? So that's what I've pictured here. That's the sub-interval within the delta theta I wedge, so that would correspond in this picture to this. Now, this is a bigger picture, so what we have that's an rij, the I is there, but let's make it clear. The sample point then would be theta sub I star, r sub ij star. So there's our sample point, and those are the coordinates. Okay? Now, this is the jth r interval within the ith theta interval, as I hope I've made clear. So this is the region that we have corresponding to a delta r and a delta theta. Okay, so what are the dimensions of this region? We want to find the area of this region, just like we'd want to find the area of a delta x, delta y interval or increment if we were using rectangular coordinates. Well, here's another picture of our interval. Clearly, this distance here is our delta rj. That should be delta rij. And that should be an ij. Okay, because the delta rij is the width of this strip here, right? And that width corresponds to this dimension of this little increment. What is this dimension? How far is it from here to here? Because if we can find that out, we can probably figure out its area. Well, I'm going to say if delta theta is small, then that should be a delta theta I, but I'm not going to correct that. We understand what that means. The straight sides are nearly parallel, aren't they? Because you got a very small angle, these two lines are going to be very nearly parallel. They don't differ by much the way I drew them, but they could be within a tiny fraction of a degree or any tiny fraction of that. So these two lines are going to be very nearly parallel, and these two sides are going to be very nearly straight because you don't have much room for the curvature to change your direction in a very small theta interval. Also, these sides are part of a radial line. Each of these sides is part of a radial line, and each of these sides or boundaries is part of a circle centered at the origin, okay? So these two are perpendicular. This is perpendicular, this is a right angle, this is a right angle, this is a right angle, and this is a right angle. But of course these things are curved, but that curvature is so tiny that we reason out that this is really just pretty much a rectangle. And as we allow the delta thetas and delta r's to approach zero, there's going to be ultimately no difference between what you get, whether you regard this as a rectangle or as a more complex shape. Okay, so in any case, the lengths of the straight sides are these. The curved sides are what? Well, they're delta theta arcs on circles of radius rj minus 1 and rj. Both of these are very close to rj star if you're letting your delta r's approach zero. So we can, without losing anything, say that, well, both of these have length about the same as the length that you would have on a circle of radius rj star. Okay? And these r's, yes, I know, have eyes on them so they can see you. Okay. This one needs an eye. I don't have the right color chalk. I'm going to put it in there. Excuse me. Okay, so in any case, an arc delta theta on a circle of radius r has length r delta theta. That's the definition of your radian. Okay, so the lengths of the curved sides are going to be rij star times delta theta I. So that the ij region is going to be an approximate rectangle with area delta ij times delta rij times rij star times delta theta sub I. And there is the area of your typical region. Now, when you set up an integral and approach a limit, that's going to become an r times dr d theta. Okay, well, next we'll consider how we then sum all of this up.